Hi, welcome back again. So far, all our functions have been explicit functions. This means they have been given by formulas of the form y equal f of x, in which the dependent variable y on the left is given explicitly by an expression on the right involving the independent variable x. The functions you see on the slide are some examples. However, not all interesting equations in x and y are given in explicit form. Certain equations in x and y either cannot be solved explicitly for y in terms of x, or can be done so only with great difficulty, and we say that they are defined implicitly. Some examples are the equations you see on the slide. We say, for example, that the function y of x is implicitly defined by x squared plus y squared is equal to 9 if x squared plus y of x squared is equal to 9. In this video, we will see how you can differentiate such functions. We start with these curves in the plane. The one on the left is the graph of a function. This means that for each x value that is involved, there is precisely one corresponding y value. The curve on the right is not the graph of a function, as you can see by looking at the vertical line, shown here for instance, which intersects the curve at 3 points. Both curves have tangent lines. The slope of a tangent line to the curve on the left can be calculated by explicit differentiation. For the curve on the right, we need another technique, which is the topic of this lecture. It is called the technique of implicit differentiation. Have a look at this example. The circle with radius 3 and center in the origin. This curve is a well-defined curve in the plane, but it is not the graph of a function, as you can see by looking at the vertical line shown here, which intersects the circle at 2 separate points. Suppose you need to compute the slope of the tangent line to the circle at one of its points. How do you do this? We don't have an explicit formula in this case, because the equation of the circle is not an equation of the form y is equal to f of x. We can divide the circle in 2 parts, which can be described by explicit formulas, namely the upper half and the lower half. The 2 functions plus and minus the square root of 9 minus x squared are defined implicitly by the equation x squared plus y squared is 9. Now suppose we want to find the slope of the tangent line at the point on the upper half of the circle. In that case, we take the explicit formula y is the square root of 9 minus x squared, and then we can compute the derivative in the usual way. And of course, we can do the same for the points on the lower half of the circle. We go back to the example of the circle. We are now going to find a formula for the derivative without actually determining explicit formulas for the function y of x first. Suppose that the y of x is implicitly defined by the equation x squared plus y squared is equal to 9. So y of x is a function that satisfies x squared plus y of x squared is equal to 9. If you look at this, everything is a function of x. So we can take the derivative with respect to x. We will do this with both sides of the equation, starting with the left hand side. The derivative of x squared is easy. It's equal to 2 times x. Now we need to take the derivative of y of x squared. Now you should pay extra attention. This derivative can be calculated with the chain rule, where the inner function is given by y of x and the outer function by x squared. The result is given by 2 times y of x times the derivative of y with respect to x. The derivative on the right hand side is of course equal to 0. Now we will rearrange things a little bit. We get that 2 times y of x times y prime of x equals minus 2 times x. We obtain that y prime of x equals minus 2 times x over 2 times y, which equals minus x over y. We can also write this as dy dx is equal to minus x over y. So we have a single formula for the derivative which is valid for all points on the circle, without having a formula for the function itself. But we also paid a price for it. The formula for dy dx contains both x and y. This technique is called the technique of implicit differentiation. Since the square root of 9 minus x squared is equal to y for points on the upper half of the circle, dy dx for points on the upper half can be written as minus x divided square root of 9 minus x squared. For the point on the lower half of the circle, y is equal to minus the square root of 9 minus x squared. And so here dy dx can be written as x divided by the square root of 9 minus x squared. So we see that implicit differentiation yields a uniform formula for the derivative which is valid for all points on the circle. Have a look at our second example we started with. This equation describes a famous curve called the volume of Descartes. As in the case of the circle, this curve is not the graph of a function. It implicitly defines several functions. Again, we could focus on a part of the curve, for example this orange part, here, which could be described by an explicit formula of the form y is equal to f of x. Unfortunately, the computation to find an explicit formula for a part of this curve are far more difficult than in the case of a circle. But we can use again the technique of implicit differentiation to compute dy dx without knowing an explicit formula, y is equal to f of x. The end result is the formula on the screen, which we leave as an exercise for you.